Okay, good morning, everybody. So I hope you had a good weekend. And then we are now, because we are now going to the last few days of the semester. I think you already finished the alternating series test and started with the power series in the lecture today. So we are about two two topics behind, but I think we're still in a good pace. Because today we'll be talking about the ratio and the root test, which is fairly mechanical. I'll go through a couple or some examples and let me know if you have some questions about these two tests, probably coming from the homeworks or the quizzes, because I think this is fairly mechanical, but they can be tricky at sometimes. I actually received a bunch of questions from my previous labs, so I think you might also encounter the same problem. So let me know in the chat if you want us to walk through some specific problems. I'll be happy to guide you through them. But while waiting for that, I'll give you a quick recap of the tests that we have so far, and then what are the essence of the ratio and the root tests. Oh, by the way, I included in this worksheet a link to a nice collection of materials. I think it was by Paul Dawkins, which is a math professor. I find his lecture notes very helpful and very informative. He also has a nice discussion there. And the nice thing is that he has materials there not only for Cal 2, but also for Cal 1, pre-calculus, calculus 3, and um, and differential equations. So if you guys want to see more examples or to read a nice explanation for this test, you can consult his website there. Actually, I lifted some of the examples he have, so we can talk about them. Now let's have a quick recap of the test for convergence and sort of an algorithm or how do you call this? A checklist or a hierarchy between the tests. What to try first and then how to go about certain series. The first thing I'll suggest is to check if it's a special series. Okay, because it's easy to spot the convergence or divergence of special series. For instance, we have geometric series, we have P series, we also had harmonic series, which we know to be divergent. And what else? We also have telescoping series, which would be convergent depending on the formula for the partial sum, right? Now, if it's not a special series, then you can try the basic divergence test. Or the BDT, right? The BDT is easy to implement. You can actually do the test in your head. You take the limit of a sub n. If the limit is not equal to 0, then it's automatically divergent. But that's the furthest it can take us, because if the limit is equal to 0, no conclusions can be made, right? So if that won't work, then you can try the comparison tests. But the comparison test, be it the direct comparison or the limit comparison test, they will require a testing series, right? That's why sometimes it's also difficult. That's why most people go to the next test, which would be the ratio or the root test. So the ratio and the root test would be extremely handy when dealing with powers and factorials. We'll remark on this more later, right? And then if the ratio or the root test won't apply, then you can try the alternating series tests. But this only works if you have an alternating series, right? So a series that alternates between a positive and a negative term. And if all else fails, or if all of these fail, then you can try the integral test. And you see, I placed integral tests at the bottom of the list because that's my last resort, because remember, for the integral test, you need to check if your series is always positive, if the terms in the series will be decreasing, and if the improper integral converges or not. So it's quite a heavy test, so that's why I put it as a last resort. Now, our topic for today is the ratio and the root test. So let's see how these two tests work. Um, let's start with the ratio test. The ratio test is extremely helpful if you expect some terms in the series, or if the terms in the series involves exponents and factorials. So this is best for ANs involving factorials and n powers, right? And here, if your series is AN and AN is positive, then you can check the limit of A sub n as n approaches infinity, or sorry, limit of A sub n plus 1 all over A sub n, and say it's equal to L, all right? If L is less than 1, then series converges. If L is greater than 1, then series diverges. If L is equal to 1, then no conclusions can be made. Okay, let's see why, at least intuitively, why the ratio test works like this. So what happens when we say that the limit is less than 1? So that means in the long run, A sub n plus 1 all over AN would be less than 1 for large n's, right? So you can multiply both sides by AN, so you'll have A sub n plus 1 is less than AN. So that means in the long run, the terms will be smaller than the previous terms. So that means the terms in your summation will eventually decrease at the ratio L, right? So since your summations towards the end will keep on decreasing, so then you will get a finite sum. That's why we say that the series will converge. On the other hand, if the limit is greater than 1, that means in the long run, A sub n plus 1 is greater than AN. So that means as you go further and further inside the summation, the terms get larger and larger. So that means there's no way you can get a finite sum, because you will just keep on adding something to the existing summation. That's why you can say that the series diverges. If the limit is equal to 1, no conclusions can be made, because that means that A sub n plus 1 will go to probably a constant value, right? But depending on the value of the constant, it can either converge or diverge, all right? So I hope that will give you a basic intuition about this test. Now, equivalent to the ratio test is the root test. They do have similar conclusions, but here we take the limit of the nth root of A sub n as n approaches infinity. All right. Now, in this case, you can also write it as the limit of A sub n raised to 1 over n as n approaches infinity. Let's call it L. And it will have the same conclusions as the ratio test. Okay, when is the root test extremely helpful? This will be helpful, or this is best for powers of n. So if you see your series to have exponents n all over the place, and you don't have factorials, then the root test is the best test to use. Okay, factorials won't work well with the root test, so whenever that's the case, then for factorials, use the ratio test. Now, one tool that we can use for the root test is that the limit. So this will come in handy for the root test. the limit of n to the 1 over n as n approaches infinity is equal to 1. So you can remember this. The solution here is using L'Hopital's rule, right? And I guess we have met this a lot of times before. So just a recall, the limit of n to the 1 over n as n approaches infinity, though it's indeterminate because it's going to be infinity to the 0. But if you use logarithms and use L'Hopital's rule, you'll see that the limit is equal to 1. Or in general, limit of n to the a over n as n approaches infinity is equal to 1. I'm not sure if this was explicitly given in the lecture. Can anybody tell me if this was mentioned explicitly in the lecture or not? Because if this was given in the lecture, then you don't need to show the work whenever you have limit of n to the 1 over n equals 1. But if it is not given in the lecture, then what you can say is that probably in your exam or in the homework, you can write somewhere that note that the limit of n to the 1 over n as n approaches infinity is equal to 1 by application of L'Hopital's rule, rather than repetitively evaluating this guy or this guy for all the root tests that you will do. Oh, so Christina don't remember seeing this in the lecture, so I guess either you compute these limits using L'Hopital's rule over and over again, which is not practical, or write this thing on top of your homework or on the top of your exam. You just need to say that using L'Hopital's rule or techniques from Cal 1, one can show that limit of n to the 1 over n is equal to 1, so that you can use this later in your solution. All right. But if it's not given in the lecture, then you cannot just assume that the grader know that you're applying this rule. So maybe it would be good to write it on top of your paper or in your in your quiz or in your exam or homework paper that this fact is established using the L'Hopital's rule. All right. So I'll keep it here because I don't want to compute that limit over and over again as we use the root test. Okay. Now let's look at some examples to see these two tests in action. Now I copy pasted here exercises from the textbook section 9.5. Okay, so you can browse through them and see if there are some interesting problems here. Just let me know if you see one. But while you're taking a look at it, I'll answer some problems or some examples here. Okay, let me start with, say, okay, let me start with this. Oh, by the way, the ratio and the root tests are equivalent. So there are cases that both of them are applicable to a certain problem, or they are of the same difficulty when applied to a certain series. The thing is that when one of those tests is inconclusive, so say if you apply the ratio test and the limit happened to be equal to 1, then do not try the ratio test because that will also be inconclusive, right? So treat of them as a single test, and they will work they will cater to the same class of series. But again, it would be helpful if you should take note that if one is inconclusive, the other will also be inconclusive, right? So let's try this first example here. I guess you can use the ratio and the root test with the same level of difficulty. Let me just try using or actually we can use both just to show you the different, how these two things apply. So first solution, I can use the ratio test. So for the ratio test, I'll take the limit of a sub n plus 1 all over a sub n. as n approaches infinity. So to get a sub n plus 1, I will look at this guy and replace all n's by n plus 1. So essentially, I'll have 10 to the n plus 1 all over. Be careful, all n's will be replaced by n plus 1. So I'll have 4 raised to the power 2 times n plus 1 plus 1. And I hope you see what I did there. Look, you started with 2n plus 1. And the deal is you change all n's by n plus 1. So this n here was replaced by n plus 1 over there. And then I added a plus 1 because I have a plus 1 there. All right. Similarly here, instead of an n plus 1, I'll have n plus 1 plus 1, right? Because the n here was replaced by n plus 1, and there was a subsequent plus 1. So I'll have n plus 1 plus 1 as the second factor there. All right. So be careful with that. You need to be mindful of changing all n's by n plus 1. And then a sub n, I'll just copy the given term and take the limit as n approaches infinity. Now I'm taking the limit of a complex fraction here. So what I'll do is to turn this into a multiplication problem. I'll put the numerator here times the reciprocal of the denominator, right? But I'll simplify it a bit. I'll have 10 to the n plus 1 all over. So I'll carry the multiplication out here. So I'll have 4 to the 2n plus 3, I guess, right? So this would be 2 times 1. So that's 2. There's a plus 1. So that would be 4n plus 3. I have a very long fraction bar there. Oh, yeah, because I have an n plus 2 remaining, right? That's for that factor. Times the reciprocal of the denominator is going to be 4 to the 2n plus 1 times n plus 1 all over 10 to the power n as n goes to infinity. Okay, good so far? All right, you can let me know by probably using the emoticons or the reactions in MS Teams, just to give you an idea that you're following. Okay, all good? Thank you, Christina. How about the others? I'd love to hear from the others. Everything's good? I hope you don't have me muted and a Netflix on the other window. Unfortunately, I did that in some of my classes, but don't be like me. Okay, now, so we simplify to evaluate the limit. And here's where you will see that this is really helpful whenever you will see that some of the factors will cancel each other out. So for instance, I have 10 to the n plus 1, and here I have 10 to the power n. So that means all of the 10s here will be canceled, but in the numerator, I will have a 10 left, right? How about for the 4s? Here I have 4n plus 4 raised to the 2n plus 1. I can cancel this by sum of the factors from 4n plus 3. So how many 4s will be left in the denominator? There would be 2 left, right? There would be a 4 squared. Because the thing here is that you will subtract the 2 exponents. So the difference would be 2. There's a larger power in the denominator. So the remainder 4 squared will remain in the denominator. And then times n plus 1 on top and then n plus 2 at the bottom. And we're taking the limit as n approaches infinity. Okay, we're taking the limit as n approaches infinity. And look at this. This would be degree 1 on top, degree 1 at the bottom. So this will go to 1, right? So because you look at the leading coefficients, leading coefficient 1, leading coefficient 1. So this guy will go to 1. So the entire limit would be 10 over 16, or that's 5/8, which is definitely less than 1. So here we say that by the ratio test, the series converges. because the ratio happened to be, or the limit happened to be less than 1. Okay, so that's how you apply the ratio test. Alternatively, you could also have used the root test. So alternative solution. And of course, it doesn't matter what test you use, you will always get the same conclusion, right? Else something is wrong with one of your tests. So here we can use the root test. Remember, for the root test, we're taking the limit of a sub n raised to 1 over n as n approaches infinity. So I'll copy a sub n. A sub n is just 10 to the power n over 4 to the 2n plus 1 times n plus 1, all raised to 1 over n as n approaches infinity. And here we will play with loss of exponents. If you are raising a power raised to another power, you multiply the exponents. So 10 to the n raised to 1 over n will be 10 to the n over n. We multiply the two exponents. Same thing goes in the denominator. I'll have 4 to the 2n plus 1 all over n times n plus 1 raised to 1 over n as n approaches infinity. All right. So if we simplify, this would be the limit of 10 to the power 1 all over. This would be 4 to the 2 plus 1 over n. So you divide this by, you divide 2n by n, you get a 2. Then you divide 1 by n, you get 1 over n. And then here I'll still have an n plus 1 to the 1 over n as n approaches infinity. Now, what happens here? Numerator is a constant 10, so that would be its limit. When n becomes large, 1 over n goes to 0. So the denominator, this guy will go to 4 to the second power. All right. And then here, n plus 1 raised to the 1 over n, using the limit I've showed you earlier, or you can also use L'Hopital's to show that this will also go to 1. So this goes to 1 by the limit I've shown you earlier. So essentially, this would be 10 over 16. Incidentally, the same limit as what we got for the ratio test. This is 5/8 less than 1. Thus, the series converges by the root test. Okay, so I guess they are of almost the same difficulty. So yeah, you could choose either any of them. Right? No questions so far? If not, then I'll proceed with the next problem. Here I'll have summation of n factorial over n to the n. Okay, here we can start at n equals 1 to infinity. All right. So here there's a factorial involved. So I guess the ratio test is the go-to test for this guy. I cannot use the root test because there's a factorial. So I'll use the ratio test instead. So using the ratio test, we'll take the limit of a sub n plus 1 over an as n approaches infinity. Now again, a sub n plus 1 is obtained by replacing all n's by n plus 1. So what will happen here is that I'll have, instead of an n inside the factorial, I will have n plus 1 inside the factorial all over n plus 1 raised to the n plus 1, right? Because all n's should be replaced by n plus 1 all over. Same thing, I'll have n factorial all over n to the n and take the limit as n approaches infinity. Now I'll write the complicated fraction as a multiplication. So I'll have n plus 1 factorial all over n plus 1 raised to n plus 1 times the reciprocal of this divisor. So I'll have n to the n all over n factorial. And I hope by now you are familiar with manipulating factorials, right? So this is n plus 1 factorial. This is n factorial. So what will be left after cancellation? Do you guys remember what happens there? Okay, great. Christina is correct. It's going to be n plus 1 left on the numerator. Again, because this is the product starting from n plus 1 times n minus 1 all the way down to 3 times 2 times 1, while n factorial is n times n minus 1 all the way down to 3 times 2 times 1. And you see that this guys will be canceled by that guy, so only n plus 1 will remain on top. All right. And then what else? So we'll have n to the n here. And then here I'll have n plus 1 to the n plus 1 as n approaches infinity. Okay. Oh, I can cancel this n plus 1 with one of the n plus 1 in the denominators or in the denominator. So I'm going to have n to the power n all over n plus 1 to the power n as n approaches infinity. Right? And then I can write this as the limit of what? As the limit of n over n plus 1 raised to the power n as n approaches infinity. And this guy is an indeterminate form, right? Because the inside will go to 1. The exponent will go to infinity. So we have 1 raised to infinity. Okay, so for that guy, I need to be a little bit careful in evaluating this limit. So I'll do the limit on a side solution here. So note, we're dealing with the limit of the form x over x plus 1 raised to the power x as x approaches infinity. So this is indeterminate because we'll have 1 raised to infinity. Okay. So what we can do here is to let y be equal to x over x plus 1 raised to the power x. And since the indeterminate form happens to have an exponent, we'll take the natural log of both sides. All right. And we do that because here I have an exponent inside the natural log. So this exponent can come down as a coefficient. So essentially, instead of an exponent there, I can have the x in front of this, right? Then when I take the limit of ln y as x approaches infinity, I get the limit of x times ln of x over x plus 1 as x approaches infinity. This would be infinity times ln of 1, right? This goes to 1, ln of 1 will go to 0, so we'll have infinity times 0, which is indeterminate. All right, and I hope you remember how to deal with indeterminate forms. So here we'll need to write it in a term in a form that is accepted by L'Hopital's rule. So here I can write it as ln of x over x plus 1 all over 1 over x as x approaches infinity. Okay, now this is of the form 0 over 0. So I can use L'Hopital's rule. L'Hopital's rule tells us to differentiate the numerator. But for that, I need to apply the chain rule. So low derivative of the high minus high derivative of the low all over derivative of 1 over x squared is negative 1 over x squared. as x approaches infinity. All right. All good so far? Lots of details there, but I hope you still follow. One thing to note here is that what we're computing is the limit of L and Y, but we were originally to compute the limit of Y. So whatever answer we get here will be the exponent for E, and that's going to be the limit, right? Okay, let's try to simplify this. Well, this will just be equal to 1. Okay, so essentially here, what we get is this. Limit of, another thing is that I have an x plus 1 squared here. It will be canceled by one of those guys. So essentially what we have on top would be 1 over x times x plus 1 all over negative 1 over x squared. Is that correct? Yeah, because this guy will be multiplied by x. So that's why I got that. I just copied this over. I guess this is correct. And then we can write it as 1 over x times x plus 1 times negative x squared as x approaches infinity. And this guy would be the limit of negative x squared over x squared plus x as x goes to infinity. And this would be equal to negative 1. All right. So therefore, what we found out here is that the limit, or this limit that we are computing, what was that limit? We started with this guy. And we said this is equal to this limit. Okay, which is equal to e to the negative 1, right? That negative 1 is from here, right? So I use that as an exponent to e, and e to the negative 1 is 1 over e, which is definitely less than 1. So by the ratio test, the given series converges. Okay. It was longer than what I expected, but I hope the process makes sense. Okay. Any questions? Everything's good so far? Oh, perhaps some more examples. Let's see. Okay, let's try example 3. I guess there's an interesting one here. Let me see. Okay, let's try 26 and 28. Okay, let's start with 26. The sum of 3 to the k times k factorial all over k to the power k. And again, this involves the factorial. So, but I think this is very similar to what we had before. Let's see. And factorial over k to the k. Yeah, problem 26 is very similar to what we had before, except that this has more factors. So I guess you can try number 26 on your own, because the process is very similar to what we did in problem 2. Let me try problem 20. 8 instead, because this is a bit more tricky, I guess. So you have 2 times 4 times 6 until 2k all over 2k factorial. Usually you don't see an index of summation here. It just means that it doesn't matter where k starts, as long as the summation goes to infinity, right? Because remember, when two series differ only by the by the first few terms, then they will either both converge or diverge. So that's why the starting index for the summation is not that material for most cases. Okay. So here I have factorial involved in the denominator, so I'll use the ratio test. Okay, and for the ratio test, we take a look at the limit of a sub k plus 1 all over a sub k as k approaches infinity. And again, be careful with the numerator. It's a sub k plus 1, so we replace all k's we see by k plus 1. So the top will be 2 times 4 times 6. Instead of until 2k, we should end at 2 times k plus 1, right? Because we are replacing all k's by k plus 1, so instead of stopping at 2k, we will stop at 2k plus 1, right? All over, instead of a 2k inside the factorial, we'll have 2 times k plus 1 inside the factorial. All right, so I replace all k's by k plus 1. The denominator is easier. I'll just copy the enter. And take the limit as k approaches infinity. Now let's turn it into a product. So I'll have 2 times 4 times 6 times 2k times 2k plus 2 all over 2k plus 2 factorial times 2k factorial over 2 times 4 times 6 until 2k. And take the limit as k approaches infinity. Now we need to identify what are the factors that will eventually be canceled. Well, it's easy to see that here the factors 2 until 2k will be canceled. So we'll be left with a 2k plus 2 here. Oops. All right. And then what does 2k factorial mean? Well, that is the product starting from 2k backwards until 3 times 2 times 1. So basically the expansion of 2k factorial is 2k times 2k minus 1 times 2k minus 2 all the way down to 3 times 2 times 1, right? That's the expansion of 2k factorial. So this guy is 2k factorial. Okay. On the other hand, the denominator has a 2k plus 2 factorial left, right? So that means we take the product starting from 2k plus 2 all the way down to 3, 2, and 1. So basically the expansion looks like 2k plus 2 times one step backward, that's 2k plus 1. Another step backward, so we get 2k. Another step backward will lead us to 2k minus 1. Pattern goes on until we reach 3 times 2 times 1. And we take the limit as k approaches infinity. Okay, and let's see what the factors cancel out. Well, I can cancel starting from where? Is it correct? Oh, okay, good. I can cancel the 2k plus 1 and the 2k plus 2 here. Sorry, 2k plus 2 and then the 2k plus 2 in the denominator. And then from 2k all the way to 1 will be canceled by 2k all the way down to 1. So what remained is what? 1 on the numerator and a 2k plus 1 in the denominator. Is that okay? And now we can take the limit as k approaches infinity easily. Numerator is a constant 1. Denominator becomes extremely large when k becomes large. So this is 1 divided by a large number. So this will be equal to 0, which is obviously less than 1. So by the ratio test, the series converges. All right. Any questions? You guys are very quiet. Have you tried any of the quiz problems or homework problems? Or you think the ratio and the root tests are very easy? Actually, they are, I think, the easiest tests because they're quite mechanical. Really, no reactions? Okay, let's try. Probably if you don't have any reactions, let me try another example. Let me look for something here. Okay, perhaps let's try problem 31. Oh, I thought they copied problem 31. I think problem 31 is this. You have the sum of root k minus root of k minus 1 raised to the power k. Let me just double check problem 31. Okay, good. All right, problem 31 doesn't have any factorial, right? And then there's an exponent k, so I'll use the root test for this guy. So for the root test, I'll need to take a look at the limit of a sub k raised to 1 over k as k approaches infinity. So this is the limit of the k term, root k minus root of k minus 1, raised to the k, raised to the power 1 over k, as k approaches infinity. And here you will realize why the root test is extremely helpful whenever the indexing variable k is present in the exponent. Because here you see that I'm raising a power to another power. All I need to do is to multiply the exponents. K times 1 over k is equal to 1. So basically, all I need to do here is to evaluate this limit. Right? Because the exponent will just be k times 1 over k, which is equal to 1. All right? But this is an indeterminate form of the form infinity minus infinity. We don't know what happens if you have an infinity minus infinity. So do you remember what did we do in Cal 1 when we had problems like this? Or you already completely forgotten what we did in Cal 1? What should I do with this indeterminate form? So I have infinity minus infinity. Obviously, L'Hopital's rule will not apply, right? Because L'Hopital's can only be applied for infinity over infinity or 0 over 0. Here we have minus Here we have infinity minus infinity, so we are subtracting two very large numbers. We don't know what will happen when we subtract those two large numbers. It depends on how large those two numbers are, right? So, okay, it seems nobody remembers, or you're just shy to answer. But for these cases, what we did is to multiply by the conjugate over the conjugate, right? So here I'm going to multiply it by root k plus root of k minus 1 all over root k plus root of k minus 1 as k approaches infinity, right? So this is valid because what I'm multiplying the given expression with is equal to 1. So this guy is equal to 1. It won't change the expression, but it will give me the better form. Remember, if I multiply this by this, I'll have root of k quantity squared minus root of k minus 1 quantity squared over root k plus root of k minus 1 as k approaches infinity, right? So all I did here is to carry out the multiplications in the numerator using special products, or you could also use the FOIL method, but essentially it will simplify to this. Now, this would be k minus quantity k minus 1 all over root k plus root of k minus 1. All right. So you just cancel the square root with the power 2 there, square root with the power 2 there. So you'll eventually get this numerator. And this simplifies to what? This simplifies to 1 over root of k plus root of k minus 1 as k approaches infinity. Okay. Now the numerator is a constant 1. The denominator is a large number plus another large number. So the denominator becomes extremely large. 1 divided by a large number is equal to 0. And 0 is obviously less than 1. So by the root test, the series converges. Okay, guys, any questions? Really, you're now creeping me out. You're too quiet. I remember during the start of the semester, you guys have lots of questions. So nobody sent me a question this time. So I think you find the ratio and the root test easy. That's why nobody asks questions. I hope that's the case. So we'll stop here. But on Wednesday, we'll talk about the alternating series tests and absolute convergence. And if time permits, we'll also go to a power series. I already uploaded a blank version of worksheet 18, which is about the alternating series test and absolute convergence. So we'll talk about that on Wednesday. And hopefully you guys will come in with your questions. All right. Okay, so that's it for today. So see you guys on Wednesday. Bye.